Welcome to CS3308 Information Retrieval. This is the Unit 3 Lecture Part 2. And in this lecture, we're going to continue our discussion about the space problem and some of the things that we started talking about in the previous lecture around compression. And we're going to kind of focus a little bit on techniques of dictionary compression. Now, if you recall in the previous lecture, Lecture 1, what we talked about was the idea that we want to try to figure out a strategy as we build our information retrieval systems that will absolutely minimize the amount of space required for our dictionary, with the objective that we can get it fit entirely in memory, because memory is very fast and disk is very slow. We also talked about the fact that we want to try to minimize our posting lists, and although we're not talking about it in this particular lecture, our postings or our document dictionary file as well, because again, disk space is going to become a premium in the sense that the data is growing so fast that we've got to be conscious of that. The other thing that we talked about was the fact that, particularly in the postings files, what we want to try to do is keep that space as small as possible. We realize it's probably too large to keep it all in memory, but since disk drives are so much slower than memory, we want to try to keep the space as small as possible on the disk, and then perhaps even use the trade-off of very high performance computing capability that we have in some sort of a decompression algorithm, such that we can maintain tiny data because it's compressed on the disk, and then use the excess CPU capacity that we have in modern computers to decompress that disk to get efficiency. Again, because what that does is it reduces the amount of data that I have to try to read from the disk drive. And as we pointed out in the previous lecture, disk drives are relatively slow when we compare them with memory. Memory operating at nanoseconds, 1/1,000,000th of a second. Disks operating in milliseconds, which is 1/1000th of a second. So the nanosecond, the memory is much faster. So let's just kind of regroup and think about why should we be compressing the dictionary. And again, keep in mind, when we talk about the dictionary, what we're talking about is the list of terms, the terms that we would be searching on. So again, search always begins with the dictionary. Okay, and the reason why is because basically what I'm doing is I'm going to go in to implement search. I'm going to give a series of terms, query terms, and those query terms is what we're going to start looking up in the dictionary. And we're going to find those terms in the dictionary. We're going to find all of the files associated within the posting list, and then we're going to go through and try to rank those documents to retrieve. So search begins with the dictionary. We want to try to keep it in memory because memory is very fast. Okay. Search systems that we're starting to put in embedded in mobile devices have even smaller memory footprints. And as you are probably well aware, we are using search technology in embedded devices. We're using them in mobile devices. If you have a smartphone, I guarantee it has a search engine in it. It is searching the data that's in there. Just think of your contacts lists, right? Basically, your contacts lists are all structured as people's names or other attributes, and you can search on it. And the way that you're able to search on it is that it's actually going out inside of your mobile phone and generating a little small embedded inverted list or inverted index. So we gotta think about that. We gotta be able to make it efficient on the smartphones of today, etc. And then even if I can't fit it into memory, so maybe I'm going to be searching the entire, indexing the entire internet, and because it's the entire internet, I'm gonna go compete with Google, for example. I can't keep it all in memory, but I still have to make it absolutely lightning fast, because quite frankly, can you imagine going to Google, sticking your terms in the website and having to wait 5 minutes for the results to come back? It's not likely that you're going to hang around and wait for those results to come back. So the dictionary has to be absolutely lightning fast, and the only way to do that is to make sure that it's either put in memory or it has to be very small so that I don't take a lot of time to read it from the disk. So all of this basically leads us to the point that compressing the dictionary is absolutely important. One would even say vital for an information retrieval system. So how do we do that? So there's a number of techniques, and we're just going to kind of cover them in a little bit of detail here. But imagine that I have that dictionary, and we've talked about the fact that maybe the dictionary is structured in some form of a tree. Maybe it's a B tree or a binary tree. Keep in mind, if you recall, the binary tree meant that every node or every search node that I had, essentially it always split it in exactly two pieces. So if I were doing this as a binary search and I had a whole bunch of entries in here, essentially, and this is 1 and this is 100, right? It's going to go to 50 first, and it's going to say, is it higher or lower? And then from there, it's going to go to, let's say it's in the lower part, it's going to go to 25, and it splits in half every time. Binary, right? What's different in the B tree is the B tree can make logical groupings other than just splitting things right down the middle. So in the B tree, I might say, hey, it's efficient to break it into 3 different pieces and make the decision on that basis. But in either case, essentially, we're putting it in some sort of a structure such that we can search it quickly and not have to do what we call a sequential search. So what I don't want to do is I don't want to start at number 1 and go all the way down to item number 433,000 as an example. That takes a long time. So I want to be able to do this kind of a thing. Now, how do I structure that data? How do I keep that data? And what we're pointing out here is, I can do it in 2 different ways. I could do an array where I have, a whole bunch of fixed width entries. Maybe I go out and I'm going to write my code in Java, and I'm going to say, I'm going to have a char structure or a string type structure in my Java, and I'm going to make that string 28 bytes because I'm going to say, man, the typical term is always going to be less than 28 bytes. Well, the problem we have with that, let's assume that this array now needs to have 500,000 entries in it, or perhaps 1 million entries in it. I essentially have 28 bytes times 1 million, which means I'm going to be consuming a lot of space, and a lot of that space, quite frankly, is not going to be used, because there's going to be a lot of words that are going to be less than 28 characters in length. So fixed sizes don't really make all that much sense. On the other hand, strategy is often that I want to use some kind of a variable size, and that sometimes gives me a much, much better approach to making the size more efficient, because I don't have the waste of character spaces that are not used. So again, when I'm using fixed is bad. Most of the bytes in my terms column in my dictionary are wasted. They're just not used. Okay. In English, the average word is 4.5 characters in length. Other languages might be slightly different. However, in all cases, what we know is it doesn't matter. If I'm going to have a fixed width, that means I have to pick the width at essentially the high end. I have to be able to deal with a really, really large term. Otherwise, I wind up losing information. So, for example, I might not be able to handle a term such as hydrochlorofluorocarbons, which is a valid term in the scientific community, if I were to only use 20 bytes. So I might want to make it bigger so that I accommodate that. But of course, if I do, I'm wasting space. So again, I have this trade-off between size and making sure that I capture the information and the wastefulness of the space, and this is all reasons why fixed width terms tend to not be very good. So what we really want to do is find a strategy to compress the term list. And one of the ways that we do that is, instead of trying to force fit it into a traditional structure, such as perhaps a 2-dimensional array, where each of the columns in that array or the elements in that array have a fixed size, maybe the better strategy is to use something that's more variable. One approach is basically to say, hey, why don't I take the dictionary and store it as a very long string of characters, and then use some kind of a pointer that points to the next word. So, maybe I know, and let me see if I can find the words in here. So that would be a word or a term in here. And then I would have, terms that are stuck in here with pointers, such that I can kind of point into the term, but I'm not wasting all the space. So if I look at this model, it's very different than the one we looked at before, right? So if I look at the dictionary as a string, I know that I'm using an average of 4.5 bytes in English for a term. I know that I'm going to need to have a pointer, right? So I'm making the assumption, or we're making the assumption in this particular case, that I would need to have 4 bytes to have a term pointer to postings. Now, basically, what we're pointing out here is that in a dictionary, I have 2 items in it, right, that are absolutely required. One of them is the term, right? That's the word that we would be searching on. And then the second one is I have to have some way of pointing from this term to the postings file. So generally what I'm going to have here is I'm going to have a postings file, and inside that postings file is going to be all of the different postings, all of the files that this term appears in. Now, the pointer to the postings file tends to be 4 bytes. I'm going to need to have 4 bytes for it. And by the way, this information actually will be in memory. So I got the term, I got the postings file. We know it's roughly around 4.5 bytes per term, in the dictionary. And then, of course, if I'm going to use this approach, essentially what I'm saying is I'm going to say, okay, I know I'm going to have some number of bytes, and then I'm going to tell it where the next one starts at. So I wind up having a series of, kind of a linked list where I'm putting in all of the pointers so that one term actually points to the next term. So essentially, this is the data structure that I'm setting up. In this particular case, I have 4 plus 4 plus 3. Okay. That's 8 bytes that I'm using for the term. Now, keep in mind, before we were looking at a problem where we said we could use 20. We knew that in some cases it might need to be as high as 28 or even larger to accommodate special words like supercalifragilisticexpialidocious, right? We had an example there. But lots of bytes, right? So we're going to have all these bytes dedicated, and then I still need to have, on top of this, the term pointer, right? So I'm still going to have all these bytes plus the pointer. So now where we're at now is we're in a fixed model. I have a minimum of 23, more likely going to be 31. Okay, but when I use dictionary as a string, I don't try to stuff it into a fixed size format. I'm down to 8 and 3, 11, right? So dramatically smaller, half or even third of the size that we would normally see. So, what we looked at before, assuming the 20 bytes for a term plus our pointer, roughly 11.2 megabytes. Just that maneuver, just that change of using dictionary as a string has dramatically reduced the size. It's now down to roughly about 7.6. So hopefully you can see the value of using this kind of a strategy. Basically, the idea is instead of an array, using a linked list. And in the linked list, each of the terms can be a variable size. That's all we're basically saying here. Another concept is blocking. The basic idea behind blocking is that we put pointers in infrequently. So the pointer that we have in let me just go back here for a second. We had 4 bytes for the term. We had 4 bytes to point to the postings list. And then we had another 3 bytes that was going to point to the next term, right? So 7 points, 7 bytes basically for that, 4 bytes for the to point to the postings list. Okay. What we're saying here is, do I actually need to point to the postings list every time? And essentially the idea here is that perhaps what I do is I have my postings organized in such a way that I kind of point to a generic file that captures maybe the 3 terms. And then I have another one that captures the next 3 terms. So rather than having, 7, 8, 9, each with its own postings file, maybe what I do is I point to 7. And then I have another one that points to 10. I'm not actually going to store the 8 and 9 because what I'll do is I'll say, well, I know I'm at 7 and I don't have too far to scan down to 9. So if that makes sense, the basic idea is it's kind of a divide and conquer. It's a strategy that says, how can I eliminate some information here that has a really big impact in storage or our ability to scan through this quickly, and then kind of pay a little something over here in terms of the need to scan through multiple entries, but it's not too bad because maybe I'm only doing 3 or 4. And hopefully that gives you some sense of what I'm talking about. But again, this idea of blocking is don't point to every one, only point to maybe the very 3rd one or the 4th one, again, then to save the space on the pointers. And again, just some math around what that looks like and what the impact might be on the size of the block. So in other words, I'm this particular case, k equal to 4 basically says, instead of going and having a pointer to every single postings list, I'm going to have a pointer to 1, right? I'm going to have a pointer to a postings list, and that postings list will actually cover maybe 4 terms. And what that means is I might have to search down, I might have to scan, search sequentially to find the right one. But since I'm limiting how many there are, it actually doesn't take that long because this is only going to be n equal 4, right, in terms of my sequential scan or my sequential search. But on the other hand, if I can eliminate that 4 bytes across several 100,000 terms, it has a significant impact in the amount of memory.